Summary of lecture 27, positive definite matrices part 2. So here I want to talk about first this energy-based definition that we see earlier that can be expanded into some polynomial equation or quadratic equation. But before that, let's discuss here about these three different matrices, and let's see if they are positive definite or not. And you see that the only difference here is that in this element, which is in the, if I were to make it in terms of A, B, B, C, that it's only in the C part. Okay. And let's do a quick test of determinant. Okay. We see the first determinant, the sub-determinant of 1 by 1 is all positive. Okay. So that's pass our initial check. But what about the second determinant? In this one, we have 14 minus 36, which is absolutely negative. And this one, we have 36 minus 36, which can be equal to 0. And in this case, we have 40 minus 36, which is absolutely positive. So in this case, this matrix here is our positive definite matrix. And this is not positive definite, or the book mentioned about the word indefinite matrix. So I'll just put it there, indefinite. And in this case, this is our case for positive, let me give a different color, semi, okay, definite. This is where we see the weak inequality of the eigenvalue can be bigger than equal to 0, or the energy-based definition also can be greater or equal to 0, while in this case we see a strong inequality here and strong inequality here as well. Okay, so I think it's really good to just stare at it for a second, and you can tell the difference between them. And a quick test of determinant test, perform a quick test to see the definiteness of each of them. Okay, and now I want to specifically talk about these two, the case for not positive indefinite and the case for positive definite. Okay, let me delete this one first, or I'll just put it here for a second. Okay, now I want to expand this matrix into this form. So what I'm basically doing is just I'm just multiplying to the left and right by some matrix. I'm sorry, some vector. That's what I want to say. And then if you multiply them, you process them together, you will have a value of 2x squared plus 12y squared plus 7y squared. Okay, so you just need to follow this form. In case of 2 by 2, it's really simple. And for this case, you have 2x squared plus 12xy plus 20y squared. Okay. And then just quickly test. Is there some point of x and y here that you see that the value can be negative, right? And turn out there is. So if you see that if you just plug in the point of 1 minus 1 here, you see that we have a 2 plus, I'm sorry, this one should be xy. Please forgive my silly error. We see we have this minus 12, and this one have 7y, and this clearly will be some negative number, right? Minus 12 plus 9, while here we have 2 negative 12 plus 20, so it will be always positive. And I just want to see make you guys see that the only difference here is that somehow this two form some quadratic function is always have to be positive, right? And the only thing that will make these functions negative is just this part right here. So this two, the quadratic part has to be bigger, has to overcome whatever the value, and especially the coefficient that is attached here in this part. Okay, so let's now see like geometrically how they will look like. And in this case, that's my first point actually here. So there's a minimum for positive definite matrix because the shape of this equation, the graph, will look like a bowl. So if I were to draw this, so I have the x, let's put it here, my x and y. Okay, and this is my function f(x) of y. Then this will look like this, completely like this. So for like 0, 0, we have point at 0, obviously, and then it will go upwards like this. Will go upwards in this, yeah, like completely like a bowl. We have a bowl of cereal right there. So we have that minimum point. But here, what happened is that okay, let's say for 0, 0, you will also have here, of course, you'll have this point at 0, 0, but it will not shape like a bowl, as we know that it has some negative value even somewhere here, like for example in the 1 minus 1, like here it goes like this, but then in some direction it also goes upwards. So Professor Strang also drew this in the lecture, that it somehow looks like this. So for some point it goes downward, and for some point it goes upward. So it's called the saddle point. Okay, and this is the case where sometimes it can go negative and sometimes it can go positive. And this is what happened in case of your matrix being not positive definite, as the name implies as well. You know, it's not positive definite, it's not definitely positive, so sometimes you have the negative. Okay, so that's just geometrically how it looks like in the plane. Okay, and there's a case to a test to see if our matrix has the minimum, which is by using the second derivative matrix. And I want to bring you attention here first. It's really similar to the calculus, you know. So let's say you have a function of f(x) equal to something, and then you want to find the optimal value, the minimum or the maximum. You do the derivative of it, and then you equal it to 0. So you find the x is equal to something, right? But then you actually don't know whether this value here is the minimum or the maximum. Okay, and then what you do is that you do the second derivative here, and then if it's positive, then it will tell you you have a minimum value, then, or if it's a negative, then you have the maximum value. And why is it for positive you have the minimum value? Because if you remember, we have kind of this function, see, this is x squared, and we have the positive second derivative positive value, is that because slowly our gradient here, our gradient of the second derivative is increasing, right? We're going from like negative slope, negative slope, negative slope, negative slope, and then we turn into some positive, 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 positive slope. And that's why the second derivative of positive value is associated with the minimum point. And that's just a quick review of this calculus. And now let's actually see how it goes here. Let's use this example and let's plug in those numbers, let's do this matrix. Let me delete some of this first. Okay, so we have this function of xy, fxy, and let's compute the second derivative to the x, second derivative to the y, and this two also. So the fx is 4x plus 12y, so we have the fxy is equal to derivative to y, so we only have 12, and the fxx is just 4, right? And for the y part, let's do the fy first. Fy is equal to 12x plus 40y, and then for the fyx, we have the 12 only with derivative to y, and then we have derivative to x. Yep, it's gone. And then fyy, we have 40. Okay, so if you put it in this matrix here, this number, and this number, we have fxs 4, 12, 12, 40. And we see quickly from the determinant test that 4 times 40 minus 1, completely it's like 44160 minus 144. Yep, it's completely positive, and this is positive definite, obviously. So it's a good sign, because in order for this matrix, this equation to be positive definite, then this is what we need to solve right here. So if the fxy has minimum, if the derivative of x and derivative of y at x and y is 0, and s is positive definite. So we have that first requirement here, the s being positive definite, and we just need to plug in some value of x and y, and we know obviously at x and y equal 0, 0, then this will be equal to 0 and 0. So the fx will be 0 and the fy will also be 0. So this matrix, with using this test for the minimum, we know that the second derivative matrix fulfills all its conditions. Therefore, this equation is positive definite. And that's it about part 2. And in part 3, let's talk about the ellipsoid. Thanks, guys.